Hi, video 5D. So we are now in the second half of module 5. And today we're going to talk about something new. We're going to talk about a mole. A mole is not this time referring to a little animal, nor is it referring to a little brown spot on your face, but it is referring to a specific number of something. Again, a mole refers to a specific number of something. So just like a couple of things refers to 2 things, and a dozen things refers to 12 things, a mole refers to that many things. 602 with 21 zeros behind it. In other words, or in scientific notation, 6.02 times 10 to the 23rd. A mole equals 6.02 times 10 to the 23rd. And yes, you do have to memorize that number. You will have to know what a mole is. Now, the reason that we need to have a mole be equal to such a huge number is that usually we are referring to a mole of atoms or a mole of molecules. And because atoms and molecules are so tiny, we need a giant number of them in order to talk about a sample that we could actually see. All right? A mole is also called Avogadro's number. It's named after the scientist who discovered it. And a mole represents how many atoms are in a sample of an element, when the mass in grams equals the element's atomic mass in AMU. Remember, we can find the atomic mass on the beloved periodic table. And let's break this down and talk about what this means. Okay, a mole represents how many atoms are in a sample of an element when the mass in grams equals the element's atomic mass in AMU. Let's take carbon, for example. If we look at the atomic mass for carbon, the atomic mass is 12.0. That means that 1 atom of carbon equals 12.0 AMUs. That's how much it weighs. Remember, an AMU is super duper tiny. Okay? So if we talk about a mole of carbon atoms, a mole of carbon atoms is equal to how many carbon atoms? That's right. We would have 6.02 times 10 to the 23rd carbon atoms, and guess how much it weighs? This is the exciting part, the little connection. A mole of carbon atoms weighs, that's right, it's the same as the atomic mass, 12.0 grams. Okay? Let's write that down and see if it makes any more sense. So, an atom's mass in AMU, okay, so just like carbon, we saw that carbon's atomic mass in AMU was equal to 12.0, and an atom's mass in AMU equals
10.
How many grams, not 10, equals how many grams are in 1 mole, and notice that mole is often abbreviated MOL, because think of the time that you're going to save by not writing the extra little e. Okay, so this is how we abbreviate mole. Equals how many grams are in 1 mole of those atoms. Okay? For example, let's see if I can squeeze an example down here. The atomic mass of boron, which is abbreviated with just a capital B, equals 10.8 AMUs. Okay, so one boron atom is equal to 10.8 AMUs. That's its mass. Okay? This also means that in 10.8 grams of boron, there are, guess how many atoms? You got it.
10.
Not 10. 6.02 times 10 to the 23rd atoms. Okay? So the atomic number that you see on the periodic table can tell you two things. It can tell you, one, how much one atom of that element weighs, or it can tell you how much a mole of that element weighs in grams. Okay, moles also can talk about how many molecules there are. Okay, so similarly to what we wrote to an atom's mass, a molecule's mass in AMU, and you would find out the molecule's mass in AMU by adding up the individual atoms that are present in the molecule. Okay, a molecule's mass in AMU, which you find out from the periodic table, is equal to how many grams are in 1 mole of those molecules. Okay, so again, the atomic masses that you find on the periodic table can tell you how much one atom weighs in AMUs, or it can tell you how much 1 mole of that atom or that molecule weighs in grams. So, for example, the atomic mass of CH4, which is called methane. A methane molecule, one of them, weighs 16.0 AMU. And I found that by adding the atomic mass of carbon, which is 12, plus 4 hydrogens. Each hydrogen is 1.01, okay? So I got the atomic mass for this molecule, 16.0 AMUs. This means that in 16.0 grams of CH4, there are how many molecules of CH4? 6.02 times 10 to the 23rd. So in 16.0 grams of CH4, there are 6.02 times 10 to the 23rd molecules of CH4, okay? Which is the same as saying 1 mole of CH4. All right, let's take a look at a figure in your book, figure 5.3, which is on page 147. Figure 5.3 just gives you an example of how much of a mole of some different substances would be, substances or mixtures. For example, here is water, okay? Water has a molecular mass of 18.0, which means that in 1 mole of water molecules, it would weigh 18.0 grams. So you can see how much water there is. That is a mole of water molecules. Okay, next you see a mole of sodium chloride molecules. Next you see a mole of iron filings, which we just used in our most recent lab. And a mole of helium. So that just the figure gives you an idea of how much a mole looks like. We use this huge number of a mole so that we have a big enough sample of these teeny tiny little particles to be able to talk about. Now let's do an example. Take a look at example 5.6 on page 148. Example 5.6 says, how many moles of fluorine atoms exist in a 50-gram sample of fluorine? Okay, so in example 5.6, we are looking for how many moles of fluorine atoms. Okay, so we're going to start with what we know. We know that we have a 50.0 gram sample. So we have 50.0 grams of fluorine. We want to use the factor label method. We want to get rid of grams, and we want to convert to moles. Okay, we don't want to know how many grams of fluorine atoms we have. We want to know how many moles of fluorine atoms we have. So grams goes on the bottom so that grams will cancel out. Moles goes on the top so that our answer is going to end up in moles. Now, do we know a ratio of how many grams are in how many moles of fluorine atoms? Yes, we do, thanks to our very favorite table. If you look at your periodic table, fluorine has an atomic mass of 19.0. That means that in 1 mole of fluorine, there's 19.0 grams of fluorine. So you fill in the numbers with the appropriate units, okay? And now we are ready to multiply. 50 divided by 19.0 is going to equal 2.63. We're doing a division problem, and so we end up with 1, 2, 3 significant figures here, 1, 2, 3 significant figures here, so we end up with 3 significant figures in our answer. 2.63. In our units is moles of fluorine. So in a 50 gram sample of fluorine, there are 2.63 moles of fluorine atoms. Okay, one more example. Example 5.6, again, the second part of it, says, people are encouraged to limit their table salt, NaCl, intake to 5.000 grams per day. How many moles of sodium chloride is that? Okay, so we are this time looking for how many moles of sodium chloride. So we start with what we know. 5.000 grams of NaCl.
Wait, Mommy.
Yes, my dear?
When you're done, can I cuddle on that board? Then you can cuddle, Mommy.
Yes, when I am done, then you can use the whiteboard.
Then you can play with me.
Yes, good girl. Okay, so we have 5.00 grams of NaCl. We're going to multiply it by grams on the bottom and moles on the top. So now we need to know how many grams are in 1 mole of sodium chloride. So we go to our handy dandy table. For sodium chloride, we have to look at Na and Cl. So Na is 23.0. I'm just going to write it on the side over here. 23.0 for sodium. And then for chlorine, Cl, 35.5. So we're going to add these together. There's 1 sodium and 1 chlorine. Okay?
Mommy.
So we get
Mommy.
58.5
Mommy.
is the molecular mass
Mommy.
for NaCl. What?
Is Claudia here?
She is here. We're almost done. Okay, so in 1 mole of NaCl, okay, so we just found that in 1 mole of sodium chloride, there would be 58.5 grams of sodium chloride. So now we multiply or divide it out, and we get an answer with significant figures are right here, 1, 2, 3, or 1, 2, 3, 4. So our answer has to have 3 significant figures. This 1 is an exact integer, so it does not figure into our significant figures, okay? And the answer would be 0.0855 moles of NaCl.